Hi, welcome to the second part of the video on forces and drawing free body diagrams. This time we're going to use the cart as the object instead of the can of Zep. At any rate, we're going to start off with the simplest one and relate back to the other ones. This cart is sitting on the floor at this point, and it's just sitting there. So I'm going to draw a free body diagram for the forces on the cart at this point. By the way, if you watch the video, make sure on Remind you text me the secret code word. The secret code word is Halloween surprise. That's a secret code phrase anyhow. But anyhow, Halloween surprise. So send me that and I'll know you watched. At any rate, right now, if I think about the cart, I'll draw a big dot there. I don't know if it looks big or not. I want to draw an arrow down, and that's force of gravity on cart. Force of gravity on cart. When I think about the upward force, it's got to be the same amount because the cart's not going anywhere. In this case, what is it? Well, the only thing acting on the cart is the floor. So, force of floor on cart. In this particular case, the next one, I'm actually going to be pushing down on the cart. You can actually see the cart deform a little bit. Pushing down pretty hard. And I'm not light. So, in this case, while I'm pushing down, what we have to think about is the force of gravity on the cart hasn't changed because it's the same cart and it's made of the same stuff. But I'm pushing down on the cart. So what does this turn into? Well, it's me pushing down. I don't know if it's longer or shorter than this. I think it's probably a bit longer because I pushed pretty hard. And I'll draw that arrow at the end of this arrow. And I'll say that's Forrest. Cart. That sounds naughty. It's not. But right now, these two forces down, if I look at it, are that big. My force upward has got to be larger than that. In fact, the only force acting upward is the floor on the cart, but it's got to be equal in size to both these arrows. So I'll draw that as a really large arrow. About like that. So this be equal to both of these. Hopefully that makes sense since the cart's not accelerating up toward the heavens or down to the center of the earth. The forces up and the forces down have to be balanced. Right? Gravity's always acting on the cart, so I'm going to leave that right there. But now, what I'm going to do is I'm going to lift up on the cart. I'm not going to pull it off the ground, but I'm going to lift up some. Both here with my hand directly on the cart and here with the string, so you can at least see that there's some tension. So if you're ready, you may or may not be able to see, but my hands have a little bit of a mark on them, so you can tell I was actually pulling up pretty hard. Not enough to lift it off the ground, which is what this would be, but quite a bit. All right, so let's think about that. What's acting downward? Well, gravity's still acting downward. What's acting upward? Well, I'm pulling upward. How much? Well, I can't be pulling up more than this is acting down, otherwise the cart would have accelerated or changed its motion and moved up off the ground. So I've got to be acting less than that. I'm not sure exactly how much, but I'll say something like this. And again, that's me, force of Forrest on cart. Well, what else? Well, the floor is still acting on the cart. And just like last time, the amount that the floor pushes on the cart can change depending on what other forces are going on. So I would think of this as my force downward, and this is my current force upward. The difference there, like this, would be the force of the floor on on cart. So once again, this would be equal in size to this. Upward forces equal to downward forces. Not that exciting. Right, the next demo is going to be a series of 3 demonstrations. And what's going to end up happening is we're going to have an initial, and a middle, and a final type of free body diagram. So initially, what I'm going to end up doing is I'm going to end up pulling this cart. Right? So what I've got here is I've got this where you can see there's some tension, so I'm definitely pulling on it, but it's not yet moving. That's the initial condition. The second or middle condition is when I'm pulling on this and it starts to move. And then the third condition is when I'm pulling on it and it's just moving at a constant speed across the ring. So we're going to have this as conditions 1, 2, and 3. So I'm going to label those as 1, 2, and 3. Of course, my marker is somewhere. We have this as 1, pulling, but not moving. 2, pulling, starting to move. And third, pulling, but moving at a constant speed. So those are going to be the 3 free body diagrams we're going to draw. All right, so here we go. So this is condition number 1. This is condition number 2 and 3. Right? So condition number 1, where I'm pulling and not moving it, I know I've got some forces here. I'm going to try to draw a big dot. Hopefully you can see that. Maybe I'll put this on this part so you can get in a little bit closer. Yeah, it works a little bit better. So in this particular case, we know we've got force of gravity down. We know we've got the force of the floor up. In fact, that's not going to change for any of these. I probably could draw those for all 3 of them right now. Force of floor, force of gravity. I'm getting lazy here. You really should label the whole agent-object notation. I'm going to try to move these kind of quickly. So, at any rate, at this point, I'm pulling to the right. I don't know how big it is. I'm going to call it that size. And again, that's tension. You could say that it's force of Forrest on cart, but I'm acting on the string. It doesn't really matter either way. But this thing wasn't moving yet. So there's got to be another force on this thing. Because right now, this shows unbalanced forces. And we know that unbalanced forces mean a change in motion. The motion wasn't changing yet. So we've got to have another force to the left. The question would be, what the heck is that? And it's got to be equal in size to this. Most of you right now have probably figured out that that's friction. Friction is an interaction with a surface. It acts parallel to the surface. And it's one of those things where it is going to be, think of that as friction on cart. And these are all on cart, on cart, on cart. So it's going to be acting against there. Friction can act on an object when it's moving or when it's not moving. So in this case, here, we've got friction on the cart. Here, when it's moving, it's just starting to move. It's actually accelerating to the right. So I probably still have some friction because you can hear the wheels rolling. So I'm going to say that's still there, force of friction. And my pole probably got bigger. Now friction could have also gotten smaller. The tension of the string definitely had to be larger than the friction on the cart. What about this? What about once it got moving? Well, once it was moving, if it's going at a constant speed, then my tension and my friction force have to be the same again. And I don't know exactly what size they are, but they should be the same size. So whether you call that large or small doesn't matter. I'll say something like this: tension and friction. The up and down forces are always the same. Okay. So we've got one more force still to go. And I'm going to back off with this so you can visualize it again. We're going to do something similar to what we did before with the cart, except now I'm going to be pulling up at an angle. Okay. So in this particular case now, I'm going to pull up at an angle, but the cart is still going to be moving at a constant speed across the floor. So I'm not interested in when I start moving it. So ready? Something like this. Okay. So again, I'll move this up so you can see a little bit better. So what do we have here? Well, we're going to start with the things we know. The pretty obvious thing that we know is gravity. That acts downward. Let's say force of gravity on cart. Well, what else is acting on it? Well, the string is acting on it. And I want to make sure I draw that string arrow in the direction that it's being pulled. So it's going to be something like this. And I'm going to call that tension. And it's acting up and to the right. Well, am I done? Well, I can't be done. So when I look at this, my downward arrow is bigger than my upward arrow, and I've got part of this arrow is going to the right, and part of the arrow is going up. My upward part isn't very big here compared to this, and my rightward part isn't balanced by anything at all. And yet the cart was going at constant speed. So if we're going at constant speed and we have no change in motion, that tells us that we have balanced forces. So despite this is pretty complicated, I've got to have balanced forces on it. Well, you might be able to recognize that if tension is going up and to the right, the thing that's going to be going to the left is friction. We've seen that before. So I would label this like this. It would be the same size as the horizontal component of this tension force. And notice we're talking about components again because we've talked about vectors already. So I'm going to say this is force of friction. And again, these are all on cart. On cart. All right, what else is going on? Well, we're almost done with this. Now, you might realize that the floor is still acting on the cart, and think about drawing the force of the floor up like this. Because what we've seen so far is that the normal force, which is a perpendicular force, coming from the floor is always the same size as gravity acting downward. But the problem in this case, well, we actually haven't seen that because when I lifted on the cart, it changed. What we have in this case is we've got a force already going upward to some extent. And if I add this vertical component of the tension force and this full length of the floor pushing up, I would have an extra force up compared to my downward force of gravity, and that cart would be accelerating toward the heavens, and I didn't see that happen. So I've got to shrink this back down. I've got to make it so that the combination of this arrow up and this arrow up would equal to that arrow down. I'm not exactly sure how big that is. I don't have to be perfect about it. But I will make this a little longer. So this is a total of about 24 centimeters down. This is a total of about 11 centimeters up. This is a total of about 13 centimeters up. So I'm going to label this force of floor on cart. So now I've really only got 4 forces acting on the cart, even though the diagram looks pretty complicated. So I'm going to get rid of these dashed lines because they help me figure out the sizes of the arrows, but they're not separate forces in and of themselves. They're just components of the tension force. So to recap, we've got a gravitational force down. We've got frictional force acting to the left. We've got a tension force acting up and to the right. And we've got the floor acting straight up on the cart, but the force of the floor is less than the force of gravity because the vertical part of the force on the floor up and the vertical part of tension acting upward would equal the force of gravity downward. So this is a scenario where we have balanced forces up and down, balanced forces left and right. And I think that's it.